I have to be honest with you, when I opened the packet for today's deep dive, my first instinct was to just close it immediately and pretend I never saw it.
That bad, huh?
I mean, it looks like hieroglyphics. We've got upside down A's, backwards E's, Greek letters, and formulas that look longer than my grocery list. We are talking about first order logic inference today, which sounds like something you'd need a PhD just to pronounce, let alone actually understand.
It does look intimidating on the page. I will absolutely give you that. It is dense. But here's the secret. This is actually the engine room of artificial intelligence.
It's engine room, yeah.
Yeah, if you think of AI as a sleek car, the chat part that everyone is so excited about right now is the paint job and the dashboard. But what we're looking at today, this is the transmission. This is the literal gears grinding together. This is how we get a machine to move beyond just spitting back facts and actually start thinking, or, well, at least mimicking the process of logical deduction.
So we're essentially popping the hood today.
We are popping the hood. And the goal of this deep dive isn't to make you do math. It's to understand how we build algorithms that can answer almost any question you throw at them. Provided, of course, that the question actually has an answer.
That feels like a very specific legal disclaimer, provided it has an answer.
It is. And trust me, that little disclaimer is going to come back to haunt us later in the hour. It leads to some pretty existential places regarding what computers can and cannot do.
Well, before we get to the existential dread, let's start with the basics. We have talked about propositional logic on the show before. That's the simple stuff, right?
Right. Think of propositional logic as the language of specific facts. It's very rigid. You can say it is raining or it is not raining. You can say John is a king.
Simple enough.
But it lacks variables. In propositional logic, you can't easily say something general like, if it rains, everyone outside gets wet.
Why not?
Because in that system, everyone doesn't exist. You would have to write a specific rule for every single person. If it rains, John gets wet. If it rains, Mary gets wet. If it rains, Bob gets wet.
Oh, I see. So if I have a database of 1,000,000 people, I literally need 1,000,000 rules just to say they get wet in the rain.
Exactly. It's incredibly inefficient, and it's brittle. If a new person is born, your logic system breaks until you manually add a new rule for them.
That sounds like a nightmare to maintain. So the mission today is to upgrade from that rigid system to this first-order logic.
Correct. First-order logic gives us variables. It gives us those upside-down A's, which mean for all, and those backwards E's, which mean there exists. It allows us to say, for all X, if X is a king and X is greedy, then X is evil. One single rule covers every king in the universe, past, present, and future.
Okay, that is much better. And speaking of greedy kings, the source material actually starts with a bit of folklore to set this up.
The greedy king problem. It's a classic in computer science.
So the axiom is all greedy kings are evil.
A sentiment that has stood the test of time, I think.
Probably fair. So if I tell you that rule, and then I tell you two specific facts, John is a king and John is greedy, you, being a human with a working brain, immediately know what?
That John is evil.
Right, you didn't even have to think about it. But, and this is the part I really struggled with when reading the notes, why is this hard for a computer? If I say all greedy kings are evil and John is a greedy king, why doesn't the computer just get it?
Because the computer sees the rule as all greedy kings X are evil. And then it sees the fact John is a greedy king. To the computer, strictly speaking, X and John are entirely different symbols. It doesn't inherently know that John is allowed to step into the shoes of X.
It's like the computer is saying, I have a rule for X, but who is this John guy?
Exactly. We need a mechanism to bridge that gap. We need an algorithm that says, aha, John is a valid substitute for X. And that bridge is what we call inference.
Okay, so we are going to look at 3 ways to build this bridge today. We've got something called forward chaining, something called backward chaining, and then the big boss at the end, resolution.
That's the roadmap. But before we get to those highly efficient methods, we actually have to talk about the first attempt AI researchers made. It was a strategy called propositionalization.
Which sounds like propositional logic with extra steps.
That is literally what it is. The early researchers thought, well, computers are really good at that old simple logic. They are really fast at checking if A, then B. So why don't we just take these fancy first-order logic rules and turn them back into simple facts?
Wait, isn't that going backward? You just told me writing a rule for every person was horribly inefficient.
It is inefficient. But it's conceptually simple. They use a rule called universal instantiation, or UI.
Universal instantiation. That sounds like we're birthing a galaxy.
It does, doesn't it?
Yeah.
But it's actually more like filling out a roster. The rule says, if you have a statement that is true for all variables, like all greedy kings are evil.
Mm.
You are allowed to substitute any ground term for that variable.
Ground term.
Just a specific name. John, Richard, the table, the chair, literally anything in your database.
So the computer just starts spamming names into the rule.
Basically, yeah. It looks at the rule, all greedy kings are evil, and it generates, if John is a greedy king, John is evil. If Richard is a greedy king, Richard is evil. If the table is a greedy king, the table is evil.
It generates a rule for the table.
It generates a rule for everything it knows about. It strips away the variables and replaces them with every single object in the knowledge base.
But that's just brute force. That seems incredibly wasteful.
It is heavily wasteful, and it actually gets worse. You also have the flip side, which is existential instantiation.
Yeah.
That deals with there exist sentences. Like, there exists a crown on John's head.
Okay, so we know there is a crown, but we don't know exactly which one it is.
Right. We know something is there, but we don't have a specific name for it in the database. So to turn this into simple logic, we have to give it a name. We invent a new constant symbol.
Like crown number 1.
Exactly. We call this a Skolem constant, named after the mathematician Thoralf Skolem. It's like a placeholder or a claim ticket. You know when you check your coat at a museum?
Yeah.
You get a little plastic tag? That tag isn't the coat, but it represents the coat. The Skolem constant is that tag.
Okay, so we generate millions of rules for every person and object using universal instantiation, and we make up names for all the unknown stuff using Skolem constants. Now we have a massive pile of simple facts. Can't we just run our old software on it?
You can. And for small problems, it actually works. But there's a trap, a fatal flaw.
What's the flaw?
Functions.
Function. You mean like math functions?
Logical relationships. Let's say your knowledge base has a concept of father. So you have a rule. Everyone has a father.
Okay.
And you have John. So applying the rule, you deduce father of John exists. Let's call him Bob.
Okay, so now we have Bob.
But the rule says everyone has a father. So Bob needs a father.
Ah, father of Bob.
And the father of Bob needs a father.
Father of Bob.
And then father of Bob.
Oh no, it never stops.
It never stops. If you try to propositionalize everything, if you try to generate every possible specific fact, you end up with an infinite set of sentences. You literally cannot write them all down. Your computer memory fills up and the system crashes.
So the brute force method isn't just slow, it's mathematically impossible if you have these recursive relationships.
Well, here's the fascinating theoretical twist. There is a famous theorem from 1930 called Herbrand's theorem. Jacques Herbrand proved that if a sentence is actually true, if the answer to your query is yes, then there is a finite proof.
Wait, I thought you said the list of sentences was infinite.
The list of possible sentences is infinite, but Herbrand says that if a proof exists, it will be found in a finite subset of that list. So you don't need to generate all of them at once. You just need to generate the first layer, check for a proof, then generate the second layer, check for a proof.
Okay, so we just keep digging deeper layer by layer until we find the answer?
Yes, the answer is yes.
I don't like the way you said if. What if the answer is no? What if John is not evil?
Then the computer will keep generating layers forever. Father of father of father, looking for a proof that literally doesn't exist. It will never stop. It will never tell you no. It will just loop until the heat death of the universe or you pull the plug.
That is deeply terrifying.
It's the halting problem. Entailment in first-order logic is what we call semi-decidable. We can write a program that says yes if the answer is yes, but if the answer is no, the program might just hang indefinitely.
So we have a system that works, but if we ask it a false question, it might just stare at us blankly for eternity.
Welcome to the absolute limits of computation.
I can definitely see why the researchers in the 60s wanted a better way. This propositionalization stuff sounds like a massive trap.
It is a trap, so they came up with lifting.
Lifting.
The idea is simple. Instead of grinding everything down to specific constants immediately, why don't we just reason with the variables themselves? Why generate if John is a king and if Richard is a king? Why not just keep the rule as if X is a king and only plug in John when we actually need to?
So we lift the reasoning up to the abstract level.
Exactly. We use a rule called generalized modus ponens. You remember regular modus ponens?
Yeah.
If P implies Q and we have P, then we have Q.
Right. If it is raining implies wet, and it is raining, then wet.
Generalized modus ponens is the turbocharged version. It says we can apply the rule even if the facts don't match exactly string for string, as long as we can find a substitution that makes them match.
And that substitution process, that's what the notes call unification.
Unification is the secret sauce. It is the core engine of all modern automated reasoning.
Okay, let's dig into this. Unification. The notes define it as finding a substitution theta that makes two different logical sentences look identical. To me, that sounds like a matching game.
It is exactly a matching game. Think of it like a lock and a key. The rule is the lock. Everyone knows X.
Yeah.
The fact is the key. John knows Jane. Can we make the key fit the lock?
Sure, if we say X equals Jane.
Exactly. You have unified them. You found a substitution, X for Jane. Now let's try a slightly harder one. Sentence A is knows John, X, meaning John knows someone. Sentence B is knows Y, Bill, meaning someone knows Bill. Can these be the exact same sentence?
Okay, let me visualize this. We have John knows X and Y knows Bill. If I make X equal to Bill and I make Y equal to John, then both sentences become John knows Bill.
Boom. You just ran a unification algorithm in your head.
Yeah.
The substitution is X for Bill, Y for John.
That feels satisfying. But I noticed a warning in the text about variable clashes, something about standardizing apart.
Yeah, this is a very practical problem. Suppose one rule uses the variable X to mean a person, and a completely different rule uses X to mean a car. If you try to unify them, the computer sees X and thinks it's the exact same object. It tries to make the person equal the car.
Which is nonsense. It's like if I'm talking about a riverbank and you're talking about a money bank and we start arguing because we're using the same word for entirely different things.
Perfectly put. So the solution is standardizing apart.
Right.
Before we start unifying, we just rename the variables. We change the second X to X17 or X new. Now there's absolutely no confusion.
Simple enough. Now, there is another term here, MGU, the most general unifier. Why do we care about being general?
This is about keeping your options open. Let's say you want to unify John knows X with John knows Z.
Okay. John knows someone and John knows someone else.
We could unify them by saying, okay, X is Fred and Z is Fred. That totally works. Both become John knows Fred. But why Fred?
Yeah, where did Fred even come from?
Exactly. By choosing Fred, we have artificially restricted the truth. Maybe John actually knows Mary. By locking it down to Fred so early, we might prevent ourselves from finding the real answer later. So the most general unifier is the substitution that makes the fewest commitments. In this case, the MGU is just X equals Z.
We just say X is the same as Z.
Right. We don't say who they are. We just say they're the same person, whoever that turns out to be.
Yeah.
We leave the variable as a variable.
That's smart. Don't guess until you absolutely have to. Now, there is one last thing about unification that sounded a bit technical, but the notes say it's crucial. The occur check.
Ah, the occur check. This is the absolute bane of efficiency. Imagine I ask you to unify the variable X with the term S of X. Now, S of X is a function. Let's say S stands for successor of. So S of 1 is 2. Can X be equal to S of X? Can a number be equal to its own successor?
No. 1 cannot equal 2.
Right. But in logic, if you just blindly substitute, you say, okay, X becomes S of X, but wait, look at the right side. It has an X in it. We just said X is S of X, so we have to plug it in again. Now it's S of X.
But there's still an X inside.
Plug it in again. S of X.
It's a snake eating its own tail. It's an infinite loop.
Exactly.
Yeah.
Logically, no finite term can contain itself, so the unification should fail. But here is the rub. Checking for it. Sending inside every single term to make sure the variable doesn't appear there is incredibly slow. It takes a massive amount of computing power.
So what do the programmers do?
They cheat. Most systems, like the famous Prolog language, just skip the occur check entirely. They assume you, the programmer, are smart enough not to ask such a stupid question.
They just turn off the safety protocols.
They do. It makes the system much faster, but theoretically unsound. It's like driving a race car without a seatbelt. Faster, lighter, but if you crash extremely hard.
Okay, so we have our tools. We have generalized modus ponens to lift our reasoning, and we have unification to match the variables. Now we need to put them into a strategy. The text outlines two main strategies, forward chaining and backward chaining. Let's start with forward chaining. The notes call this the reactive detective.
Forward chaining is data-driven. You start with what you know, the literal facts on the ground, and you let those facts trigger rules to generate new facts. You keep doing this until you solve the mystery.
And we have a literal mystery here, the Colonel West case. This seems to be a standard example in AI textbooks.
It is the hello world of inference.
Okay, let's solve it. Here are the clues we have in our database. 1, it is a crime for an American to sell weapons to hostile nations. 2, the nation Nono has some missiles. 3, all of Nono's missiles were sold to it by Colonel West. 4, West is American. 5, missiles are weapons. And 6, an enemy of America counts as hostile. We also know Nono is an enemy of America. Goal is to prove West is a criminal.
All right, let's run the forward chaining algorithm. Iteration 1. The computer looks at the base facts. It sees No-No has missiles and West sold No-No's missiles. It unifies these and deduces a brand new fact. West sold missiles to No-No.
Okay, putting pieces
It
together.
also sees missiles are weapons, so it deduces the missiles No-No has are weapons. And it sees No-No as an enemy of America, so it deduces No-No is hostile.
So that's the first pass. We've learned some new things. Now we run it again.
Iteration 2. The computer looks at the new facts we just generated. It sees West as American, which is from the start. The things West sold are weapons. He sold them to No-No. And No-No is hostile. Does this match any big rules?
Yes. The first rule. American plus sells weapons plus to hostile nation equals crime.
Bingo. All the conditions are met. The rule triggers. The system stamps a new fact into the database. Criminal West. The goal is found. Proof complete.
That feels very natural. It's how I would solve a puzzle. I lay out the pieces and see what fits together.
It is natural. It's fantastic for monitoring systems. Imagine a security robot. It sees motion in hallway. It sees time is 3 a.m. It triggers the rule alert guard. It reacts to incoming data.
But wait, if I have thousands of rules and millions of facts, doesn't this get incredibly slow? Does the computer have to check every rule against every fact every single time it learns something new?
That is the ultimate bottleneck. If you do it naively, the system crawls to a halt. That's why we have the RETE algorithm.
RETE. R-E-T-E. The notes say it means net.
Yes, Latin for network. I want you to imagine a giant Plinko board or maybe a really complex system of water pipes. At the top, you pour in the facts. The nodes in this network are the specific conditions of your rules.
Okay, visualizing the pipes.
Let's take the rule American ND weapon ND hostile. When the fact West is American drops in, it hits the first node. It passes. It flows down to the next node, which is waiting for weapon. But maybe we don't know about the weapon yet, so the fact just sits there in the pipe. It waits. It doesn't disappear. And crucially, we don't have to recheck, is West American ever again? We've already done that work.
I get it. It remembers partial matches.
Exactly. It saves the state of the system. Then, 10 minutes later, the fact missile is a weapon drops in. It flows down, meets the waiting West, is American fact, and they move together to the next stage. This makes it incredibly fast because you are only processing the changes.
That makes a ton of sense. So this RETE algorithm is what makes things like real-time AI possible.
It was a massive deal in the 80s and 90s. It powered production systems like XCON, which DEC used to configure computer orders. It saved them millions of dollars. And it's the basis of cognitive architectures like SOR.
The notes mention SOR. It models human memory.
Yeah. They try to essentially mimic the structure of the human mind. The facts currently in the RETE network are like your working memory, what you are thinking about right now. The rules are your long-term memory. As you perceive the world, facts hit your working memory, trigger rules from long-term memory, and produce new thoughts.
So forward chaining isn't just an algorithm, it's a theory of cognition.
Yeah.
But there's a downside, right? You mentioned it can generate junk.
Oh, massive amounts of junk. Forward chaining is entirely indiscriminate. It derives everything it possibly can. In the Colonel West example, while it was figuring out he was a criminal, it might have also deduced West owns a pair of shoes. Or No-No is a country with dirt, if those facts were in the database. It doesn't know what is relevant to your goal. It just knows what is legally true.
It's a blabbermouth that tells you everything, even if you just asked, is he a criminal?
Right. So to fix that, we have magic sets.
Magic sets. Now we're definitely in fantasy territory.
It is a terrible name for a very cool database concept. Basically, it's a filter. You want to know, is West a criminal? Magic Sets takes that goal and rewrites the rules backwards just for a second. It says, okay, to prove criminal, we need to know about West. We need to know about No-No. It creates a magic set of relevant facts. Then it runs forward chaining, but only on those relevant facts.
So it puts blinders on the detective. Ignore the shoes, focus on the missiles.
Precisely. It combines the hyperfocus of goal-directed reasoning with the efficiency of data-driven reasoning.
Which brings us nicely to the other side of the coin. Backward chaining. If forward chaining is the reactive detective, backward chaining is what? The planner.
The planner, the strategist. Forward chaining asks, what can I learn from these facts? Backward chaining asks, how do I prove this specific goal?
So let's look at Colonel West again. Goal is West a criminal.
The system starts with the absolute goal. Is West a criminal? It looks for a rule that concludes criminal. It finds criminal if American AD sells weapon AD hostile.
So it breaks the big goal into sub-goals.
Yes. Now it has a to-do list. 1. Prove West is American. 2. Prove West sold a weapon. 3. Prove the buyer is hostile. It checks number 1. Is West American? It looks in the database. Yes, it's a fact. Check. Now number 2. Did West sell a weapon? It doesn't find that fact directly, But it finds a rule: missiles are weapons. So now it has a new sub-sub goal. Did West sell missiles?
It's working perfectly backwards from the conclusion to the raw evidence.
Exactly. This is much more focused than forward chaining. It only explores things directly relevant to the question you asked.
This is how the programming language Prolog works, right?
Yes. Prolog is legendary. Its core motto is algorithm equals logic plus control. You, the programmer, provide the logic, the facts, and rules. Prolog provides the control, this backward chaining search. You don't tell Prolog how to find the answer. You just vividly describe the world and ask a question.
That sounds perfect. Why don't we use it for literally everything?
Because Prolog has a blind spot, a very dangerous one. It uses depth-first search.
Meaning it dives down the first rabbit hole it sees.
And sometimes that rabbit hole has no bottom. The classic example is finding a path in a graph. Imagine you want to go from point A to point Z. You have a rule. There's a path from X to Z, there's a path from X to Y, and a link from Y to Z.
Sounds logical to go somewhere far away, go to a midpoint first.
But look at the rule again. To find a path, look for a path. It is fundamentally recursive. If Prolog tries to solve path A to Z, it says, okay, I need to find a path A to Y. To solve path A to Y, it says, okay, I need to find a path A to another Y. It keeps diving deeper and deeper, looking for a path to a path to a path.
Without ever checking if there's just a direct road right next to it.
Exactly. It can get hopelessly trapped in an infinite loop just because of the arbitrary order you wrote the rules. It is logically correct, but computationally broken.
So how do we stop the infinite loop?
One clever way is memoization, also called tabling. It's basically giving the computer a notepad. Every time it solves a sub-goal, it writes it down. I already checked if there's a path from A to B. The answer was no. If it loops back to that exact question again, it sheps the notepad instead of blindly diving back in.
Like a cache.
A cache. It prevents the system from doing the exact same work twice and cleanly stops many of those infinite loops.
The notes also mention constraint logic programming, or CLP. Is that related?
It's the powerful evolution of Prolog. Regular Prolog wants to find a specific value, x equals 4. CLP allows constraints. X is greater than 4. Think of a Sudoku puzzle. You don't solve it by guessing numbers one by one. You say this square can't be 5 and must be greater than 2. You narrow down the possibilities. CLP allows variables to be ranges or relationships. It's incredibly powerful for complex scheduling and logistics.
Okay, so we have forward chaining for data, backward chaining for planning. But the notes say these methods have a serious limitation. They mostly handle definite clauses. If A and B, then C. But what about negation, if not A, or disjunction? A or B is true.
That is exactly where the specialized tools fail. Forward and backward chaining are lightning fast, but they are brittle. They can't handle, maybe. They can't handle or. If you tell a forward chainer, either Jack or Curiosity killed the cat, it completely chokes. It doesn't know what to do with that ambiguity.
So we need a heavy hitter, the nuclear option. Resolution.
Resolution. This is a sound and complete algorithm. If an answer exists anywhere in the logic, resolution will absolutely find it. It can handle negation or not everything.
And it works by proof by contradiction. I remember this from high school geometry class. To prove something is true, you assume it's false and see if the world explodes.
Basically, yes. You assume the negation of your goal. Then you mix it with your known facts. If you derive a contradiction like x is 5, a and d, x is not 5, then you know your assumption was wrong, and the original goal must be true.
But before we can use this resolution rule, we have to do something, well, something pretty unpleasant. We have to convert everything into CNF, conjunctive normal form.
Ah, yes, the dreaded bureaucracy of logic. Resolution is a very simple mechanical rule. It only works on sentences that look a highly specific way. So we have to take our beautiful, readable, logical sentences and smash them into a flat, ugly, standardized format.
The notes describe this process, and it sounds like absolute torture. You have to remove implications.
Yes, you can't say if P, then Q. You have to change it to not P or Q.
Yeah.
Logically, they're identical, but the second one is much harder for humans to read, and you have to move all the knots inward, and you have to scolemize all the variables.
It's like breaking a beautiful Lego castle back down into individual flat bricks just so you can store them in a standardized box.
That's a great analogy. CNF is the box of bricks. It's just a long list of clauses combined with A and D, and each individual clause is a list of literals combined with OR.
Once we have our box of bricks, how does the resolution rule actually work? The notes say if we have A or B and we have not B or C, we can conclude A or C.
Think of it as algebraic cancellation. You have A or B, you have not B or C. Whatever B is, it's either true or false. If B is true, then not B is false. So for the second sentence to be true, C must be true. If B is false, then for the first sentence to be true, A must be true. So no matter what happens with B, either A or C holds, we can just cancel out the B's.
We resolve
We
them.
resolve them. We smash the two clauses together and get a new, simpler clause. And the whole game is keep smashing clauses together until you produce an empty clause.
An empty clause.
If you resolve P with my P, what is left? Nothing. That literal nothingness is the contradiction. It means your premises were fundamentally incompatible. You've formally proven the impossibility.
Okay, I think I get the abstract idea, but we need to see this in action. We have a mystery in the notes. Curiosity killed the cat. This is a complex one. Let's look at the facts. 1, everyone who loves all animals is loved by someone. 2, anyone who kills an animal is loved by no one. 3, Jack loves all animals. 4, either Jack or Curiosity killed the cat whose name is Tuna. And 5, Tuna is a cat and therefore an animal. Question, did Curiosity kill the cat?
All right, let's try to solve this intuitively first. What does your gut say?
Okay, well, Jack loves all animals. So Jack is a nice guy. Usually nice guys aren't animal killers, so I'm going to guess Curiosity did it.
That's a good human heuristic, but it's not a mathematical proof. Can you formally prove it?
Well, let's see. If Jack killed a cat, then he killed an animal. Rule 2 says anyone who kills an animal is loved by no one, so no one loves Jack. But Rule 1 says everyone who loves all animals is loved by someone, and Jack loves all animals. So someone does love Jack. Wait, Jack is loved by someone, A and D loved by no one.
Contradiction. You found it. If Jack killed the cat, we hit a total logical impossibility. Therefore, Jack did not kill the cat. And since Rule 4 says either Jack or Curiosity...
Curiosity is the killer.
Exactly. You just performed a complete resolution proof in your head. The computer does this formally. It converts everyone who loves all animals is loved by someone into CNF. Which, by the way, involves that Skolem function we talked about, replacing someone with a function like level of X. We can't use a constant because someone depends on who the animal lover is.
Right, everyone has a different someone.
Exactly. Then it converts the goal Curiosity killed the cat into not Curiosity killed the cat. Then it starts smashing. It resolves Jack killed Tuna with no one loves killer, resulting in no one loves Jack. It resolves Jack loves animals with someone loves animal lovers, resulting in someone loves Jack. It resolves no one loves Jack with someone loves Jack, resulting in the empty clause. Boom. Proof.
It's ruthless. It really is the nuclear option. But the notes mention a specific problem area for resolution, equality. Why is X equals Y such a massive headache?
It seems so simple to us humans. If I tell you Superman is Clark Kent, you instantly know that if Superman can fly, Clark Kent can fly. You substitute them freely. But logic is intensely liberal.
Right.
It doesn't know that the equal sign is special. You have to explicitly tell it everything. Like what? Like X equals X, reflexivity. If X equals Y, then Y equals X, symmetry. If X equals Y and Y equals Z, then X equals Z, transitivity. If X equals Y, then function of X equals function of Y for every function. If X equals Y, then predicate of X is same as predicate of Y for every single predicate.
Oh my God. You have to define the very concept of sameness entirely from scratch.
Yes, and that creates an absolute explosion of rules. The computer starts substituting X for Y everywhere it possibly can, generating millions of totally useless variations.
So how do we tame it?
Specialized rules. Demodulation is a big one. It's a simplification rule. If you have a rule like X plus 0 equals X, and the computer sees term plus 0, demodulation says don't even think about it, just rewrite it as term immediately. It aggressively cleans up the mess.
And pair modulation.
That's the really big gun. It allows the resolution algorithm to reach inside a term and selectively swap equals for equals during the unification step. It's extremely complicated math, but it makes handling equality actually possible without generating infinite junk.
It seems like computationally expensive is the prevailing theme of the day. Resolution is powerful, but dangerous. So we need strategies. We can't just be random about smashing clauses. The notes list a few. Unit preference, set of support, subsumption. Let's break them down real quick. Unit preference.
A unit clause is a short sentence, just one literal, like King John. A long clause is A or B or C or D. If you resolve two long clauses, you usually just get another long clause. You aren't making any progress toward the empty clause, which has a length of 0. But if you resolve a long clause with a unit clause, the result is shorter. A or B plus Hamiltonian, not A equals B. The strategy is always prioritize the short stuff. Aim for the units. It aggressively shrinks the problem down.
Makes total sense. Print the tree. Next is set of support.
This one is very clever. You divide your facts into two separate piles. Pile 1 is background knowledge. Cats are animals, kings are rulers. Things we know are true and internally consistent. Pile 2 is the goal, negated. The thing we are actively trying to prove. We know the contradiction must come from pile 2 because pile 1 is just general facts. So the strategy says, never resolve two facts from pile one against each other. Only resolve things that are derived from pile two. Focus on the actual question. Don't just churn through the encyclopedia.
That seems like a massive time saver. And finally, subsumption, which sounds like something a sci-fi villain would do. I will subsume you.
It's actually just garbage collection. If I know a general rule, everyone loves ice cream. And I also have a specific fact. John loves ice cream. The specific fact is entirely redundant. The general rule covers it perfectly. It subsumes it. So throw the specific fact away. Delete it from memory. Keep the database lean.
So, to summarize our very long journey today, we started with rigid propositional logic. We lifted ourselves to first-order logic with the variables using unification. We saw forward chaining, the reactive detective, using the REAT algorithm. We saw backward chaining, the planner, using Prolog. And we saw resolution, the theorem prover, using CNF and contradiction. This is all incredibly impressive. But I have to ask, does anyone actually use this today, or is it just for solving logic puzzles about Kernel West?
It is absolutely used everywhere. The killer app for this technology is verification. Think about a modern computer chip, an Intel processor. It has literally billions of transistors. You cannot comprehensively test it by just running it. There are too many possible states. You could run it for 1,000 years and not hit the one specific bug that causes a crash.
Like the famous Pentium floating point bug.
Exactly. That cost Intel $500 million. So now they use formal logic. They write a mathematical description of what the chip should theoretically do. And they write a description of the actual circuit. Then they use a theorem prover, essentially a massively scaled resolution engine, to logically prove that the circuit matches the spec. Not test. Prove. Like a math theorem.
So they logically prove the chip is bug-free before they even build it.
Yes. It's also used heavily in software. The notes mention the remote agent on NASA's Deep Space One spacecraft. You can't exactly send a geek squad to Mars if the software hangs. They used automated reasoning to formally verify the concurrency algorithms to mathematically ensure that the threads wouldn't deadlock in space. If you fly on a commercial plane or use a secure banking app, you're relying on code that has very likely been touched by these exact logic systems.
That is genuinely comforting. It's nice to know that Curiosity Killed the Cat is actually keeping planes in the sky. But I want to end on that provocative thought from the notes. We circled around it earlier with the halting problem. Gödel's incompleteness theorem.
The absolute heavy hitter. Kurt Gödel proved mathematically that in any logical system powerful enough to do basic math, like our computers, there will always be statements that are true, but fundamentally cannot be proved within that system.
True, but mathematically unprovable. That just, it breaks my brain.
It breaks everyone's brain. The system can effectively say, this sentence cannot be proved. If the system could prove it, then the sentence would be inherently false because it says it can't be proved. That would make the system a liar. It would be inconsistent. So assuming the system is honest, the sentence must be true, it really can't be proved. But the system itself can never demonstrate that.
So as we build these AI agents, as we build these massive logic machines using resolution and forward chaining, are we essentially building them with a permanent, unavoidable blind spot?
We absolutely are. We are creating agents that will inevitably encounter profound truth they simply cannot understand. They will hit hard logical walls where the answer is objectively yes, but they can never compute the proof. They will just loop forever looking for it.
But what about us? What about humans? Can we see those truths?
That is the ultimate debate in cognitive science. Famous physicists like Roger Penrose argue that humans can see the truth of Gödel's sentences. We use intuition or insight to magically jump over the logical gap. He passionately argues this proves the human brain is not a computer, that we are doing something fundamentally non-algorithmic. Quantum, maybe?
But the alternative?
The alternative is that we are just wet computers, and that our prized intuition is just a messy, highly evolved heuristic by biological guess that happens to be right often enough to keep us alive, and that we are just as rigidly limited by Gödel as the machines are. We just don't notice the blind spot because we get distracted and go get a sandwich instead of looping forever.
On that mildly terrifying note, the idea that we might just be buggy biological software, I think we'll wrap up. This has been an unbelievable journey, from greedy kings to the absolute limits of mathematical truth.
It's a deep rabbit hole. But hopefully the listeners now have a working flashlight.
Keep optimizing your inference engines, everyone, and try not to get stuck in an infinite loop. We'll catch you in the next deep dive.